I'm basically a physicist, and I mainly worry about how a microscope works rather than what I see in a microscope. Definitely what I see is important, but rather than that, we will see how the microscope work and why this equipment is called a microscope itself. So it's very interesting, and I have used a lot of references for preparing this talk, and these are my references. And the electron microscopy part is taken from the Transmission Electron Microscopy, a textbook for material science by David Williams, Barry C. Carter, published by Springer in 2009, and other articles. All these articles are available with me, and if anybody is interested, I can share. Okay, and the topics today I am planning to cover is basics of microscopy, scanning electron microscope, followed by transmission electron microscope, and the microscopes. Why it is called a microscope is the resolution that you achieve using this microscope is of the order of 0.2 micrometers. Best, and your eye has got a resolving power of 0.2 millimeters. If two objects are at a distance of 0.2 millimeter, your eye will be able to say, we have two objects. Okay. Otherwise, when you use this microscope, your resolving power is increased to from 0.2 micrometers, 0.2 millimeters to 0.2 micrometers. Okay, micrometers is 10 to the power of -3. So here you have an augmentation to improve your resolution. That is why you call it, and it is in micrometer range, and that's why you call this equipment a microscope. So the microscopes are instruments designed to produce magnified visual or photographic images of small objects, and the microscope must accomplish 3 tasks mainly. And first is it forms a magnified image of the specimen, separate the details of the image, and render the details visible to human eye or a camera to make a photograph. These 3 are the main objectives of the microscope. And this group of instruments includes not only multiple lenses, very sophisticated Leica type of microscopes, but even a handheld magnifying glass is a microscope. Okay, so that also improves. And light microscopes, which are limited by the physics of light, that its magnification should be 500 to 1000 magnification and resolution of 0.2 micrometers. People will think, why this 1000 magnification? I will, within a few slides, I will explain to you scientifically why this 1000 comes. Okay, so the principle of the microscope is very simple physics. Says it starts from a convex lens principle. You know, everybody knows what's a convex lens, and when you put an object in front of the convex lens, you will get an image on the other side. If you keep the image at the focal plane, at the focal point, you will get a same size image at the focal point on the other side. On the other hand, if you keep the image away from the focus, you start getting magnified images. And the magnified image, there's a formula relating the focal length, the object distance, and the image distance as 1 by p plus 1 by q is equal to 1 by f. P is object distance, q is image distance, and f is the focal length. And we have the expression for magnification as q by p, the ratio of the image distance to object distance. Very simple expressions which you would have studied in the school. And we have another important aspect of resolution, the resolution, and I call it as the Rayleigh criterion for resolution as resolution R is equal to 0.61 into lambda divided by numerical aperture, and I want this resolution to be the smallest possible value. For this to be smallest possible value, what should increase? Either numerical aperture should increase or lambda should decrease. We know that our visible light, is having 300 to some 700 nanometers. Average you take 300 nanometers. Okay, when you have 300 nanometers, put this numerical aperture as equal to 1. What will happen? 0.61 into 300 is equal to almost equal to 250. Isn't it? Nanometers will be the resolution. 250 into 10 to the power of minus 9 meters is the resolution. Okay. So this resolution is not very high. This resolution, as I told, will become equal to almost 2.2 micrometers. Okay, this is equal to almost 0.2 micrometers. And why you cannot increase the resolution using the optical microscope is mainly because of several aberrations that the lenses have. We have several types of aberrations or defects, and these defects causing lot of problems to the images, and these are called as aberrations. And mainly we have on-axis lens errors called as chromatic and spherical aberrations, and we have off-axis errors called as coma, astigmatism, and field curvatures. And the third class of aberrations commonly seen in stereo microscopes and zoom lens is the geometrical distortion, which includes pincushion distortion, barrel distortion, and moustache distortions. We will see all these defects and see what are they. For example, the spherical aberration. If your lens is having finite size, the rays that are getting transmitted through the extreme ends will be focusing at different points. Okay, at different points. So instead of having one point as focal point, you are having a region of focal points. Okay, and this extends the focal points, and this is spherical aberration. Whereas chromatic aberration, what happens is when white light comes, it disperses into different colors, and different colors focuses at different points. Therefore, see, for example, we have spherical aberration, as I told you. This can be, see, instead of having one point focused, it is having a line, a length of illuminated line is seen here. Here, this is the aberration is minimum. See, the top, we can see that top we have negative spherical aberration. Middle top we have a negative, center 0, and bottom we have positive spherical aberration. All these spherical aberrations are present. And look, the chromatic aberration, the photograph taken, our resolution is not that good. So you can see that different colors are coming on different parts. Here you have red fringes, you can see. Okay, these are all as a result of chromatic aberration. And see, when you are having spherical and chromatic aberrations, your object looks very blurred, and it is not in focus, and it looks, see, sometimes this color green looks violet, and this sharpness of the image is lost because of this aberrations. And it's not simply this explanation of this. These are having specific values also, and this is mathematically connected. For example, if the lens has got R1 and R2 as the curvatures of two surfaces, we can have a shape factor called C, which is equal to R2 plus R1 divided by R2 minus R1, and we call it as Coddington's shape factor. On the other hand, if you are having the image position and object position at P and Q, which I have written here as I and O, then the Coddington position factor is defined as I plus O divided by I minus O. The spherical aberration will be such that the C, the Coddington condition for minimum spherical aberration is that this C, R2 plus R1 divided by R2 minus R1 should be equal to minus 2 into n squared minus 1 divided by n plus 2 into P. That means where n is the refractive index. Therefore, what is the result of this? Result of this is that, see, I have a lens having focal length 10 centimeter. So, if my shape factor varies from minus 2 to plus 2, my focal length will vary from 9.2 centimeter to 9.9, about 0.8 to 0.9 millimeter elongation is there on your focal length. This is the problem with the spherical aberration. So, you cannot have one fixed position, a range of positions where your focal length is visible. This is what is the relation between this the spherical aberration. Okay, spherical aberration is a mathematical quantity. Therefore, the other defects also we can see that, see, for example, this off-axis coma aberration. For example, look at the rays from, see, in this what happens is, when you project the image of a point object, instead of seeing one spot as a magnified spot, you start seeing a coma blur, something like a what is known as a comet. Okay, this is coming because different zones on the object. Topmost part of the object forms an image at the center. Zone 2 just below that forms just outside that, and zone 3 means still down it forms another circle, and zone 4 forms another circle near extreme, and as a result you will see a series of circles one after the other forming a coma blur. Apart from this, you have a field curvature problem. For example, a flat specimen, when you image it, you see that the extreme ends of the object looks curved, and this is the field curvature aberration. And among these classes, one of the important one is astigmatism, and because astigmatism arises because of the fact that the rays traveling at extreme, see, for example, the horizontal and the horizontal ends of this red rays, they are focused at one point. Okay, and we call it as tangential focal plane where these rays meet. Okay, and the rays on the horizontal positions or horizontal extremes, these are rays on vertical extremes. Rays on horizontal extremes I have shown as yellow, and this focused at another point called a tangential focal plane. Sorry, I missed it. And the other one is called a sagittal focal plane. Okay, for this horizontal one, it is a tangential focal plane, and the vertical ones, it is called a sagittal focal plane. So, you have two different focal planes for horizontal extreme rays and vertical extreme rays, and in between you have a plane called the circle of least confusion. For example, imagine an airy disk. It is nothing but a series of concentric disks. This airy disk, when projected with a lens having astigmatism, in tangential focal plane, the image looks like this, not at all circle. Look, it is very much distorted, and this looks like this. Here on sagittal focal plane, it looks totally different. Look, it looks that this image is 90-degree rotated. Okay, and in the plane of circle of least confusion, it looks like an airy disk. So, between sagittal focal plane and tangential focal plane, you have a point called a circle of least confusion, where you will be getting that image. Therefore, all these defects contributes to the it prevents forming better image using a lens. Therefore, you can see this. See, this is blurring due to astigmatism. Look, When I am trying to focus this, central portion is nicely focused. Is the extreme portion focused? No, it's out of focus. Similarly, when I try to focus that extreme ends, center become out of focus. Okay, this is called as blurring due to astigmatism. And I told you that curvature effect. Look, this curvature effect, a series of illuminated spots when viewed through the microscope. Look, these are all elongated, whereas center is remaining as such. This is because of field curvature effect. Clear? Yeah. And this is the geometric distortions. Look, these are the, see, I'm viewing a grid. When there is no distortion, it really looks like a grid. But when there is a barrel distortion, the extreme ends become curved convexly curved, like a barrel. Okay? Whereas in the pincushion distortion, it curves in the inwards. Okay, in a concave way. Then you call it as pincushion distortion, and when you are having both pincushion and barrel together, you call it as moustache distortion. Okay, or wavy distortion. Okay, and these distortions really limit the resolution and better viewing of the images in the microscopes. And when there is no such things, wave diagram for a perfect lens shows that a train of parallel rays coming and hitting the lens should produce one exact focal point. Okay, and exact focal point when there are no that is known as aberrations. And here I have given defined again the condition for resolution. Resolution I defined as 0.61 into lambda divided by numerical aperture. Here I am defining the numerical aperture. Numerical aperture of a lens is defined as n into sine theta, where n is the refractive index and sine theta is the semi-angle of collection of the rays. For example, when your objective is very near to your specimen, the angle through which you collect the rays is very high. Then theta will be naturally very high, and when you are keeping the lens at low magnifications and low resolutions, you will be having theta much less. For example, here theta is 32 degrees and numerical aperture is 0.6. Here it is 48 degrees and numerical aperture is 0.8, and here it is 58 and the numerical aperture is 1.3 for a refractive index of 1.515. Okay, therefore I have projected it properly. See, I have used here as mu for theta. So when there is mu is 7 degrees here, then numerical aperture is 0.12. When it is 20 degrees, numerical aperture is 0.34, and when highest magnification resolution, numerical aperture is 0.87. Therefore, when we use numerical aperture is equal to 1, there is no harm, no problem. It's a good approximation to explain you what is this microscope. I have used numerical aperture 1. So numerical aperture can be 1. Okay. Therefore, now the resolution I have defined as wavelength divided by numerical aperture, and here I am going to explain you why a magnification more than 1000 is not possible. As I told you, the maximum resolution possible in an optical microscope is 0.2 micrometers. That is equal to 0.2 into 10 to the power of 0.2 into 10 to the power of minus 3. Am I right? What is your eyes resolution? 0.2 millimeters. That means 0.2 into 0.2. The micrometer is 0.2 into 10 to the power of minus 6. whereas your millimeter is 0.2 into 10 to the power of minus 3. What is the magnification you can get here? Magnification is nothing but the size of the image divided by size of the object. Am I right? Then what will happen is, in the case of this, when you observe it using a microscope with your eye, your resolution is 0.2 into 10 to the power of minus 3 divided by 0.2 into 10 to the power of minus 6 ratio of your resolution powers. This will become 10 to the power of 3, which is equal to 1000. That is why I am telling you scientifically that no resolution, no magnification other than 1000 is possible for an optical microscope, and any magnification more than 1000 will become only magnify the image without getting proper resolution, and this resolution is called as empty resolution. Empty magnification. Any magnification above 1000 in an optical system is called as empty magnification, no meaning. You are only magnifying. You then use a Xerox machine and go on magnifying it 100 times, 100% each. Will it be giving any more information? No, it will not. Okay, so theoretical limit is there for your resolution. That is why you are saying that magnification of your optical microscope is limited to 1000. Now I will tell that, after a few slides I will tell you that maximum magnification with proper resolution for an electron microscope is 10 lakhs, 1 million. Okay, that also I will prove through this type of what is known as this from the definition of this magnification. Okay. And can you have better resolution? The best possible resolution is possible when you are having from your object to your objective is having same refractive index. That is why you use some oil immersion, what is known as oil microscopes. You see, you have specimen, above that you have cover slip, above that you put an oil in between your objective and the cover slip, so that your rays travel through the medium of same refractive index throughout. This will improve the magnification, resolution. Okay. And the oil is also given in such a way that oil, covering slip, all these things are selected in such a way that they have same refractive index. Otherwise what will happen is bending of rays will occur and resolution will be still poorer. Okay. And you have two types of microscopes. One is finite tube length microscope, and the ray paths I have shown here. For example, it has got an objective. Objective produces an image in the intermediate image plane, which is viewed by an eyepiece, and you get the final image. Here what happens is the rays from the objectives directly fall on the intermediate objective plane, and your object is placed in such a way that it is either at the focal plane or from the focal point to the pole, in between this distance, so that it always forms a what is known as diminished image, and this is viewed through the eyepiece. Whereas on the other hand, if there is an intermediate lens, here if the lens is produced at the focal point, then what happens is output of this will be a set of parallel rays, and this parallel rays, when focused by another lens to an intermediate focal plane, what you are seeing is the image of the object formed after making the rays parallel. When rays are parallel, we assume in optics that these parallel rays are coming from infinity. Therefore, we call it as this microscope as infinity corrected microscope. Or even though your object is at finite position, we in between we introduce the condition of infinity by putting this at very close to the objective, between the focal point as well as the pole, and then producing a train of parallel rays which you focus onto the intermediate image plane, and then you view using an eyepiece so that your final image is being viewed or photographed. This is called as infinity corrected microscope. Am I right? And why we have done all these things, there is a reason. For example, I will tell. Now, look, here I have shown is a series of diffraction gratings. You would have done in physics practical classes. Diffraction grating. What is this? These are all transparent objects with series of parallel lines drawn. And here the first one has got 50 lines per millimeter. Okay. The second one is called as 100 lines per millimeter. Third one has got 300 lines per millimeter, 600 lines per millimeter, 1200 lines per millimeter. We can have diffraction grating with two different what is known as pitch, line spacing, also together. For example, the 50 and 100 together you can have on one grating. Upper side having 50, lower side having 100. That is also possible. Okay. So, series of lines are drawn on this diffraction grating. If you put a diffraction grating on the stage of your specimen stage and see the image, what will happen? I will show that. For example, let there be no image on your microscope stage. What happens? You have your light source, okay, and that aperture is also there above that light source. And this aperture will, the image of the aperture you can see through your eyepiece. Am I right? On the other hand, if I keep this diffraction grating with 50 lines per millimeter on the stage, specimen stage, immediately instead of having one image, you started getting 3 images. One is the direct image you already got, even without grating, and 2 other images, and these images are all dispersed. Colors are dispersed. Okay. And if I move the number of lines in the gratings to a higher number, that means I told that keep the 50 lines per millimeter grating, got 2 images. Immediately I can shift to 100 lines per millimeter grating, that part. Immediately you got 4. Remove that grating, put a grating with some 600 or 1200 lines per millimeter, several images. Okay, several images you start observing. Why? Why? The reason is that the direct image you are observing is the undeviated light, whereas the other images you are observing is because of the deviated light. There is a path difference between the light travelled directly and light travelled in an angular direction, and because of this path difference it produces a phase difference and it produces constructive or destructive interferences depending upon the position. Depending upon the path difference occurs, and hence at different positions, and because of this image is dispersed also. Okay. So, instead of having one image, you are getting a series of images. For example, if I keep this large spaced grating, you get this image. You closer planes, you get more number of images. And you, instead of having this, you put a square pattern, square grid. Okay, immediately the image also responds. You got 3, 9. Okay, and instead of square, a triangular grid is put. You got perfectly hexagonal type of images. That means the images which are the magnified ones of objects, this image B, D and F is orthoscopic image, and the images A, C, E and G is called as conscopic images. So, 2 types of images are possible in a microscope. Orthoscopic image, you may be viewing almost every time this orthoscopic image, whereas there is a possibility for you to depending upon the conscopic image, and the conscopic image is nothing but a what is known as an indication of the symmetry of your objects, and this is called as diffraction pattern. Okay, so your conscopic images are always diffraction pattern depending upon the symmetry of your object. So object magnified, symmetry of the object projected, both are possible. Okay, object magnified is the basic function of the microscope, plus symmetry is also reflected. This is what we call as the function of a conscopic image. Orthoscopic image you always see, whereas conscopic image you rarely see, because see, the microscope when it is designed, both will be formed. But the problem is, the designer of the microscope always makes sure that it won't form at the same point. Both are formed at the same point means lot of confusion. So what we do is, we project the orthoscopic image to an intermediate image plane and view through your eyepiece. Whereas to see the this conscopic image, you have to remove the eyepiece, put a telescope. Telescope also will be available with your Leica or any other microscope. Then this telescope will focus to the principal focal plane of your objective. So on the principal focal plane of your objective, what is formed? The conscopic image is formed, that is viewed using an eyepiece. Whereas to an intermediate object, the image plane, you are projecting your orthoscopic image and generally taking that image. You are happy. You are getting a magnified image. Whereas this is also possible. This possibility is very well used in electron microscopy. Because, see, here I have put lines, grids, line spacing as the object to produce diffraction pattern. Whereas in an electron microscope, what I am using is interatomic spacing as the grid, as a what is known as diffraction grating. Atoms are sitting in lattice in a perfect arrangement. Interatomic spacing I am using because the wavelength of the radiation used is comparable to and this spacing, this interatomic spacing is comparable. Whereas here, is it comparable? No. Atoms interatomic spacing is not comparable with your wavelength. That is why I put a diffraction grating. Okay, diffraction grating with 50 lines, 100 lines, 1200 lines per millimeter. That is micrometers. Whereas your atomic spacings are nanometers or even angstrom units. And your radiation is also that way. So there is a compatibility. Okay, therefore, the possibility of orthoscopic and conscopic images are always possible in any microscopy, which I am going to use in electron microscopy very extensively. Okay, and this is the general section of a microscope from top and bottom. This is for transmission mode, and this is for reflection mode, and here this is for transmission mode. Sorry, this is for transmission mode and this is for reflection mode. Both are used. Okay, so for people like me, material science people, will always use it in reflection mode because we see surfaces, nicely polish the surfaces and take the images. Whereas the people in life sciences and all, they take sections and tissues and sections and then take it from the light is transmitted to that and you get an amplitude contrast image. Am I right? So both can be used. And percentage contrast is defined as Bi minus Si into 100 divided by Bi, where Bi is the intensity of the background and Si is the specimen intensity. Therefore, to have a contrast, you should have some intensity difference produced. Otherwise, you won't see the same. Okay. For example, there are several techniques by which you can enhance the contrast in your optical microscope. The first one is dark field microscopy. I extensively used it in electron microscopy also. What is dark field microscopy? See here, the illumination is made oblique, not direct. Okay, dark field microscopy. Here what happens is, your what is known as your light source or condenser is first covered with a lid, and lid having a ring. So the light is coming only through that ring, not that complete light is coming. This ring, the light in the form of a ring is then focused by a condenser lens to your specimen. So instead of having complete direct light, you are having an oblique illumination. Then what happens? You are viewing it, you have a cone of illumination, and from the objective this light is entering. Okay, and this you are viewing. As a result, what happens is, whatever is having a very bad contrast in bright field become very, very, very good looking in dark field. For example, look, this is a bright field image. You can see all background light is there white. Same when took as dark field image. Look, background is dark, and this is very useful for biology. Look, some insect, the image of an insect, dark field microscope. Look, all this hair at the end of this legs are all very clearly highlighted. Okay, this is very good for you, not for our physicists. We never use dark field. We use dark field image to view the morphology of crystals. Of course we use. But dark field microscopy is a wonderful technique where you make the illumination oblique illumination, not direct illumination. And in photography also you use it, isn't it? See, instead of having direct light photography, you use some lights at some hidden points and then take your image. It may look very wonderful. It may look wonderful. I don't know. I am not an expert photographer, but it may look wonderful. So the dark field imaging is a very useful technique. Now, you have another technique called Rhineberg Illumination. See, what is done is, here, instead of having the central portion completely covered, you have a central filter with some color.